Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to finish going through Chapter 6.3, looking at linear systems with non-real eigenvalues. In our last video, we introduced the general structure of solutions to systems with complex eigenvalues and eigenpairs. We looked at how we have eigenvalues that had components alpha plus or minus I beta and eigenvectors p plus iq. And we derived a general form for our solution of differential equations as a linear combination of a real and an imaginary portion. This is going to be the formula that you're going to need to know for completing our homework questions. And we looked at doing this with a first example, where we found our general solution to be given here. And I remember telling you in that video that most students will write our solutions in this form. We also looked at how to draw the phase portrait for such a system. And our phase portrait looked like this. We saw spirals emanating from the origin, growing in size because of our exponent e to the 5t. And we drew our null lines to determine the direction of movement of our solutions. So now I'd like to continue with this and look at a couple more examples. So let's consider this system of equations. Now in this example, I've done some of the preliminary work for us so we can focus on the new ideas presented. So consider this system given by x prime is this matrix times x. The first thing we're going to want to do is find our eigenvalues. Now I like using the trace determinant approach to find your eigenvalues. That your eigenvalues must satisfy lambda squared minus the trace of a times lambda plus the det of a. Where here, recall that the trace of your matrix must be the sum of the elements on your main diagonal. So here the trace of a is -2. And your determinant of a, remember your determinant is going to be the product of your main diagonal, which is going to be 0, minus your off diagonal, which ends up being +5. So that your characteristic polynomial, remember it's always lambda squared minus the trace. Our trace ends up being negative. So lambda squared plus 2 lambda plus 5. Since this is not factorable, we use the quadratic formula, and we find our eigenvalues must satisfy -1 plus or minus 2i. Remember here, you need to know that alpha, the real part of your eigenvalue, is -1, and beta, the imaginary part of your eigenvalue, is +2. Now we have to go look for our eigenvectors. And remember, when looking at the equation a minus lambda I x equals 0, we're always subtracting our eigenvalue off of the main diagonal only. And if you were to simplify, you get this matrix. Now when looking for our eigenvectors, remember this matrix is always singular, which means one of these rows has to be a multiple of the other. That tells us the only row we need to use is the first row. So let's look at the first row times this vector. And this will give us the equation 1 minus 2i times x plus y equals 0. It doesn't matter which one we choose, but generally what I'll do is let x equal 1. Because if x is 1, then we have the equation 1 minus 2i plus y has to equal 0. Or if we solve this for y by moving this to the right hand side of the equal sign, I think we'll get y has to equal negative 1 plus 2i. And this allows us to write our eigenvector x as the vector whose first component is 1 and the second component is negative 1 plus 2i. However, we need to write this as a real component and an imaginary component that fits this description. So remember, our real components are just the real numbers here, 1 and negative 1, and the imaginary component is going to be 0 and 2. In terms of our general formula we're going to be following for our solution, this is your p vector, this is your q vector. Now that we have our eigenvalues and our eigenvector written in terms of its real and imaginary components, we can jump to writing our general solution to the linear system. So let's first write the real component of our solution. So your x real part has to be, well, let's just look back at our general solution so we can see this again. Oh, I didn't leave it written here. You have to look at your notes. My notes, I have removed these. Okay, it's going to be e to the alpha t. So here alpha was negative 1, so negative 1t times cosine of beta t times your p vector minus the sine of beta t times your q vector. Oh, that's positive 2. And I'd like to rewrite this now as a single vector quantity. So let's distribute the cosine into this vector, the sine into this vector, and then add our two vectors together. I think we'll get e to the negative t. Now the first component of your vector is going to be cosine of t, cosine of 2t, and the second component is going to be negative cosine of 2t minus 2 sine of 2t. This is the real component of your solution. I don't know why, but it feels like I think that looks right. Okay, now let's write down the imaginary part of our solution. It's going to be e to the alpha t, so negative t. Now remember, in our general solution, it's going to be the sine term first. So sine 2t times your p vector, 1, negative 1, plus cosine of 2t times your q vector, 0, 2. And again, we'd like to write this as a single vector quantity, so let's distribute the sine term and the cosine terms into these vectors, and then add your two vectors to get e to the negative t times the first component is going to be sine of 2t. The second component is going to be negative sine of 2t plus 2 cosine of 2t. So that our general solution has to be a linear combination of these two solutions. I'm going to write it with the common factor of e to the negative t factored out. So I'm going to write this as your general solution x of t is e to the negative t times your c1 cosine 2t negative cosine 2t minus 2 sine 2t plus c2 times your second vector quantity and this is the general solution that we're looking for. Okay, now let's look at drawing our phased portrait. Now to draw our phased portrait, we need to rewrite our linear system as a system of equations. So let's take our original system given by x prime equals ax, and let's expand this and write it as a system of equations again. So here, if we let the vector x be the vector with two components, x and y, then we're going to have x prime is our matrix times our vector x. And if I expand this, this will be x prime, y prime. Our first equation that we're going to get comes from the first row of our matrix times our column, which I believe is going to be 0x plus y, so just y. And our second equation is going to be negative 5x minus 2y. So now this is your system of equations. Now let's go look for our null inclines. So remember, looking for your vertical null incline, your V null incline. On your V null incline, you have vertical slopes only. And this only happens if x prime is equal to 0. If you have vertical slopes, then your lines have to be moving up and down, which means there's no horizontal movement. X prime has to equal 0. So grab your x prime equation, which is y equals 0. This is your vertical null incline. Now let's look for our horizontal null incline. On a horizontal null incline, there is horizontal slopes only. So graphically, you're thinking horizontal null cline looks like this. But the only time you're going to have a horizontal null cline is if y prime is equal to 0. So there's no vertical movement. So grab your y prime equation. And solve for y. You'll move the negative 5 to the other side, so it becomes positive 5x, divide by negative 2, and I think you can write this as y equals negative 5 halves x. Okay. Now let's draw our coordinate system. And let's label this x and y. Okay, now maybe this is where I'd like to pause the video for a moment and give you a chance to draw your null clines, determine the direction of movement on the null clines, and the direction of movement in between the null clines. After you've done that, unpause your video, come back, and we'll see if we agree. I'll see you in a moment. Okay, I hope you paused your video and worked on drawing these null clines. Let's see if we agree. Now the first null cline I want to draw is your vertical null cline. Now on your vertical null cline, I'm expecting to see vertical movements only. And that happens along the line y equals 0. And so y equals 0 is your x-axis. And on this x-axis, we're expecting to see vertical movement only. So I'm going to represent that with a vertical line segment. I still have to determine, is my vertical movement up or down? But for now, I know that they are vertical. Along our horizontal null cline, you should see only horizontal movement. And this is on the line y equals negative 5 halves x. And so without being terribly accurate with my graph, a line of negative 5 halves x would have a slope that's negative 5 halves. It probably looks something like this. And we know along this line, slopes are horizontal, so they have to be moving like this. But to determine the actual directions of movement, let's pick some test points. On the positive side of our x-axis, a point that lives on this line might be like the point 3, 0. And I'm picking that point randomly. Now let's take the ordered pair 3, 0, and let's go back to our system of equations. If x is 3 and y is 0, then it tells us x prime is 0. And we should have already known that, because this is a vertical null cline. There are vertical slopes only, which means your horizontal movement has to be 0. If you plug 3, 0 into your second equation, notice that here that your y prime is going to end up being negative 15. And again, I don't really care that it's negative 15 as much that it is just negative, which tells me that your y movement has to be negative at that point. So at the point 3, 0, our solution curve has to be moving downwards. Now we could pick another test point at a place on the negative side of your x-axis, but I think what we wanted to recognize from our last example is that your solutions, your trajectories always change direction when you cross your other null cline, which means it should be moving up here. Okay. Now let's pick another test point on our horizontal null cline. A point that maybe lives on this null cline would have an x value, and pick an easy x value. You're looking here, like maybe x is equal to 2. But if x is 2, y has to be negative 5. Now let's go back to our system of equations and use the ordered pair 2, negative 5. Let me erase my notes I made. Now if you evaluate this at the ordered pair 2, negative 5, 2 for x, negative 5 for y, then this will be positive 10. This is negative 10 and this is positive 10. This ends up being 0. But we knew that because we're on a horizontal nullcline. You have to have horizontal slopes only, which means y prime has to be 0. When you plug in 2, negative 5 into x prime, you get that x prime ends up being negative 5. And all that I really care about is that it's negative, because it tells me at that point 2, negative 5, your horizontal movement is negative, so solutions have to be moving to the left. Now we could have picked another test point to see what's going on here, but I'd like you to know that your trajectories always change direction when you cross your other nullcline, which means here it has to be going to the right. Okay, now let's determine the directions of motion in between these nullclines. If you were to pick any ordered pair here and stick that ordered pair into your system of equations, you'll notice that you're moving to the right and down, and so in general, solutions in this region will always be moving down and to the right. If you picked an initial condition that lived in this region, you'd be moving to the left and down, and in general, down and to the left. A solution in this region, we'll be moving up and to the left, and in general, up and to the left. Lastly, a solution in this region, we're moving up and to the right, and in general, up and to the right in some way. And now I want to draw a solution curve that obeys this direction field. Looking back at our general solution, we should also recognize that our general solution has components with a negative exponent. Now this tells me that as time goes on, this term decreases and it shrinks to 0. The trigonometric portions of our vectors tells us we have cyclic motion. So what I'm expecting to see here is a cyclic or a spiral motion that decreases towards the origin. Now we'll see this when we draw our curve in here, because if I were to start at some initial position, let's say here, you'd have to move down and to the right until you eventually cross this nullcline. You'd have to cross it vertically. Then you can be moving down and to the left, eventually cross this one horizontally. Then you're moving up and to the right, cross this one going vertically. And you can imagine how this could spiral into the origin. Okay. Let's add to this example now by looking at what a phase plotter would look like. So if you could, let's go to our Canvas course. And I want to grab our phase plane calculator for systems of DEs. And let's enter in a system. Our x prime equation that we had was just x prime equals y, and our y prime equation we had was negative 5x minus 2y. And let's go ahead and click on a couple of spaces to see what our trajectories would look like. Notice how they do spiral towards the origin as time goes on. This does confirm our hand calculations that we did. Okay, let's go back to our guided lecture notes, and let's look at one more example. Now I'd like to give you a minute to work on this example on your own. I've did the preliminary work for your eigenvalues and eigenvectors, but if you could continue finding your eigenvector for me, and then let's write your general solution to the system of equations. So I'll see you back here in a moment after you've worked on this. Okay, I hope you paused the video and worked on this. Let's make sure we agree. While I did a lot of the preliminary work for you already, I do want to agree that we are on the same page. Remember, when using your eigenvalue-eigenvector equation to find your eigenvalues, or the trace determinant equation to find your eigenvalues, remember your trace is always the sum of the elements on your main diagonal. So here the trace is 0. And your determinant, the product of your main diagonal minus your off diagonal, it would be negative 16 minus a negative 25, ends up being positive 9. So with a trace that's 0 and a determinant that's 9, your characteristic polynomial looks like lambda squared plus 9 equals 0, which gives you eigenvalues of the form net plus or minus 3i. Here you need to know that your alpha, your real part of your eigenvalue, is 0, and beta, the imaginary part of your eigenvalue, is 3. Now you needed to find your eigenvectors using the equation a minus lambda I x equals 0. And for the eigenvalue 3i, remember we're subtracting this off of the main diagonal only. This eigenvalue forces this matrix to be singular. It means that one of these columns or one of these rows has to be a multiple of another. And we're going to use that by identifying that the only equation we really need is the equation that you get from this first line times this first column. So when you multiply this, I think we're going to get 4 minus 3i times x minus 5y equals 0. Now we get to choose a value for x or y, and it doesn't matter what you pick, but I would like to pick x is equal to 5 in this example. Because if x is equal to 5, then we're going to get four minus 3i times 5 minus 5y is equal to 0. Notice that we can factor out the 5 and then divide to get just 4 minus 3i minus y equals 0, or that y has to equal 4 minus 3i. This allows us to write our eigenvector x as a vector whose first component is 5 and whose second component is 4 minus 3i. However, I'd like to write this in terms of the sum of two vectors with a real component and an imaginary component. The real component would have 5 and 4 as its entries. The imaginary component would have 0 and -3. In terms of our general solution, this is the p vector that we need, and this is your q vector. Now, with this as your eigenvalues and this as your eigenvectors, we can jump to writing our general solution to our linear system. So, our real solution. Let's first write the real part. It's going to be e to the alpha t, or e to the 0t, times the cosine of beta t, times the p vector, minus the sine of the beta t, which, don't write beta, we'll put the 3t there, times your q vector, and I would like to simplify this by multiplying these trig functions into your vectors and then adding your two vectors together. Also notice that e to the 0t is just 1, so this vector is going to look like five cosine of 3t as your first component. The second component is going to be 4 cosine of 3t plus 3 sine of 3t Now the imaginary part of your solution, again, is e to the alpha t, and it's going to be the sine of 3t times your p vector plus the cosine of 3t times your q vector and again, let's simplify this by multiplying the sine into this vector, the cosine in, and then adding these two vectors together. I think we're going to get back 5 sine of 3t, and then we're going to have 4 sine of 3t minus 3 cosine of 3t. Now remember, our general solution has to be a linear combination of these two solutions. So our general solution, x of t, is going to be c1 times our first vector plus c2 times our second vector. And this is what our general solution looks like. Okay, now let's look at the phase portrait. So to write our phase portrait, draw our phase portrait now, we need to convert our system of equations that's from a matrix form to just an individual system of equations. So let's jump on that on the next page. So here, if we let our vector x be the vector with components x, y, then our system of equations look like x, y, prime. Our matrix times our x vector. Our first equation will be x prime equals 4x minus 5y. Our second equation will be y prime equals 5x minus 4y. Now, this is where I'd like to pause the video again for a moment and ask you to determine your horizontal and vertical nullines for your curve, and then look at sketching your curves. So if you could pause your video and take a look at that. When you're done, come back and we'll see if we agree. I'll see you in a moment. Okay, I hope you paused your video and looked for these nullines on your own. Let's see if we agree. So let's start by finding our vertical nullline first. Now remember, your vertical nullline has vertical slopes only. But this only happens if x prime is equal to 0. So x prime being 0 means you have no horizontal movement, which means you have vertical slopes only. And so grab your x prime equation, which is 4x minus 5y equals 0. And let's solve for y. Move the 4x over to make it negative. Divide by negative 5. I think you should get 4/5 x. Now let's find your horizontal nullline. Remember, this has horizontal slopes only. And the only way you're going to have horizontal slopes only is if your y prime is 0. So grab your y prime equation, 5x minus 4y equals 0. And let's solve for y. Of course, if you solve for y, you'll move your 5x over, which will make it negative, and divide by negative 4. I think you should get y is equal to 5/4 x. Okay, now let's draw our coordinate system. And let's label this y and x. Now I don't want to be terribly accurate here, but notice that your vertical nullline, the line negative 4/5 x, has a slope that's less than 1. And your horizontal nullline has a slope that's a little bit greater than 1. So now if I were trying drawing these, your horizontal nullline would have a slope bigger than 1, so maybe something like this. This is your h nullline. And your vertical nullline with the slope of 4/5 be a little bit less steep, probably look more like this. And I'm not being terribly accurate with by measuring my slopes, but they're approximately right. Now remember on these, your horizontal nullline has horizontal movement. And your vertical nullline is going to have vertical movement. We need to determine the direction of these movements. So let's pick some test points. For our vertical nullline, the 4/5 x. Let's pick a test point. And a nice test point might have an x value of 5, because if x is 5, then y is going to be 4. And let's go plug this order pair 5, 4 into our system. When you plug 5 into your x component and 4 into your y component, know that this is going to equal 0. And we should know it's 0 because we're plugging this into a vertical nullcline, which means you have only vertical movements, which means x prime has to be 0, and it is. When you plug in 5 and 4 into your y prime equation, this is going to be 25 minus 16. This is going to be positive, which tells you your y prime is positive at that point. Solutions here have to be moving upward. Now you could pick a test point on the other side of your curve, but I'd like you to recognize that if here you're moving up, then over here you have to be moving down. Okay, similarly, let's pick a test point on your horizontal nullcline. And because your horizontal nullcline is described by the line 5/4 x, I'd like to pick x is equal to 4. Because if x is 4, y is 5. Let's go plug these into our system. X is 4, y is 5. Let's switch these. I'll plug it into our second equation first. If x is 4 and y is 5, then now y prime turns into 0. But we should have known that because this is a horizontal nullcline. There's horizontal slopes only, which means y prime has to equal 0. And when you plug 4 and 5 into your x prime, notice that this is 16 minus 25. This ends up being negative, which tells us your x movement, your horizontal movement, has to be in the negative direction. And so here solutions are going to be moving to the left, which means here they have to be moving to the right. Okay. Now let's determine the direction of movement in each region. If you pick a point in this region, you have to be moving down and to the left, and in general down and to the left. In this region, you're moving down, to the right, down and to the right is your general movement. Here would be to the right and up, in general up and to the right. Here would be moving up and left, and in general up and to the left. Okay, now let's think about what a trajectory would look like. And before I start trying to graph it, I'm going to look at our general solution. Notice here that the exponential piece of our solutions disappeared and turned into 1, which meant that we don't have a factor that's increasing or decreasing over time. And our general solution is just a linear combination of cyclic functions. Because this exponential piece right here went to 0, it tells me that my distance from the origin isn't growing without bound or shrinking towards the origin. But I still see this cyclic behavior. This tells me that when I think about solutions that start at some point, I should not see them spiraling in or out from the origin, but more see ones that leave here, cross horizontally, come down, cross vertically, cross horizontally, and maybe look something like this. We just see ellipses that kind of rotate around the origin. Now to confirm that this is true, let's look at our phase plane plotter. And let's go change our system of equations. Here we had 4x minus 5y. Our second one was 5x minus 4y. And now let's click around to see what some trajectories might look like. And it looks like I have an error here. This looks like it's spiraling outwards, and I wasn't expecting it to spiral outwards. 4x minus 5y, 5x minus 4y. Let me see if I can fix this, because I'm expecting spirals here, by changing our step size. And let's clear our curves. And I do see them spiraling in the same direction, but it looks like they still spiral in a little bit. And I'm wondering if I change this to, say, circular orbits is what we're expecting. Now, it did change our coordinate system. I'm going to want to play with this one a little bit more, because I want this to still show the elliptical pattern that we were working with a minute ago, because this changed our equation too. There we go. Now it's showing the circular pattern that we're expecting with our differential equation that we were given. Okay, I hope this is helpful. This should give you all the material you need to complete your homework in chapter 6.3. And I'll see you again in our next video.